Hello everyone, my name is J. Jagan Ghosh from EC branch Electronics and Communication Engineering A section. This is my 80 Tech Talk video, chemistry, and my topic is about a fluidic colorimetric sensor designed for water hardness detection. Introduction. First, water hardness. There are two types of water are there. We all know that. First, hard water and soft water. Hard water are which contains salts. Water hardness is a common issue in many regions. Traditional methods for water hardness detection are costly and time consuming. Fluidic colorimetric sensor design offers a promising solution. Measurement of hardness expressed as milli equivalent per liter or mg milligram per liter. 1 milli equivalent per liter of hardness is equals to 50 milligram calcium carbonate, 50 ppm in 1 liter. Working principle: the sensor utilizes a colorimetric metric method to detect water hardness. A chemical reaction occurs between the water sample and the reagent in the sensor. The color change in the reagent is proportional to the hardness level in the water. This is the mission. This is a sample from street water, softened water, and the water hardness. These are the test results of water hardness. To next, sensor components. The sensor contains a microfluidic channel for sample delivery. A reagent chamber is included to hold the chemical reagent. An optical sensor is used to measure the color change in the reagent. And these A, B, C, D, these are the sensor components. And the C component degenerate planar surface anchoring on all channel walls and glass substrate. Next, advantages of fluidic colorimetric sensors. Faster detection compared to traditional methods. It is very faster of detection of hot water. Portable and it is very easy to use. And cost effective and requires minimal maintenance. These are the advantages: temperature visualization and black dice PDMS chamber. A new sensor designed for detecting water hardness using complexometric and colorimetric concept is presented in this paper. In this paper, Cal maggot and a metal ion indicator changes color of a solution to wine red in presence of calcium Ca2 plus and magnesium Mg2 plus ions at pH 10 value. A red solution is a transparent to a red light, whereas non-transparent to a blue light, and vice versa. A photodiode placed across the solution will give out a reading of voltage V. Variation across the diode depending on the amount of red or blue light passing through the solution and striking the photodiode. A sensor prototype is 3D printed with a channel embedded into hold with a channel embedded into hold water sample. Water hardness is detected based on visual inspection of color change of the sample and voltage change occurring when calamagate and EDTA are mixed to the sample. For a first generation prototype, voltage variation of 30% and 13% for blue light and 6% and 70% in the average. For red light in comparison to the baseline When neither calamite for EDTA is mixed to the water sample is observed due to color change, then a second generation prototype is printed which shows improvement in voltage readings compared with the first generation. Transmittance and absorbance of the solution are computed using the voltage variation data recorded across the photodiodes. A calibration curve is then compiled by measuring absorbance of various concentrations of standard CaCO3 solution, which is then used to predict the water hardness type of the water sample. Next, advantages of fluidic colorimetric sensors. These are faster detection compared to traditional methods, and these are very portable and easy to use, cost effective and requires minimal maintenance. Next, calibration. The sensor needs to be calibrated with a known standard solution of water hardness. The calibration curve is used to determine the hardness level of the water sample. The sensor can be recalibrated by periodically to ensure accuracy. The calibration. This is the graph of calibration, and the sensor can be recalibrated periodically to cal- ensure accuracy. Instrument calibration is one of the primary process used to maintain instrument accuracy. Calibration is the process of configuring an instrument to provide a result for a sample within an uh, acceptable range. Eliminating or minimizing factors that cause inaccurate measurements is a fundamental aspect of instrumentation design. Although the expect precedent procedure may vary from project to project, the calibration process generally involves using the instrument to test samples of one or more known values called calibrators. The results are used to establish a relationship between the measurement technique used by the instrument and the known values. The process is essence teaches the instrument to produce results that are more accurate than those that would occur otherwise. The instrument can then provide more accurate results when samples of unknown values are tested in the normal usage of the project. Next application, the sensor can be used in various settings, including laboratories, water treatment plants, and homes. It can be used to monitor the water quality in real time. The sensor can improve the efficiency of water treatment processes. Dissolve air flotation tank. This is the sensor mixed sludge from secondary treatment. This dewatering, dry sludge, and air tank. These are the components in a sensor design of water detection, and limitations for a hot water detection of the sensor. The sensor may not be suitable for detecting extremely high or low levels of water hardness. The reagent in the sensor may degrade over time, affecting accuracy. The sensor may not be as accurate as traditional laboratory methods. TDS water conductivity sensor used to measure the TDS value of water. High sensitivity and easy to use plug and play. Future developments. The future developments of the fluidic colorimetric sensor designed for water hardness detection. The sensor can be further improved by incorporating advanced materials and technologies. Efforts are being made to make the sensor more selective to water hardness ions. The sensor can be integrated with a wireless monitoring system for remote monitoring. And the conclusion, Fluidic colorimetric sensors offer a promising solution for detecting water hardness. They are cost effective, easy to use, and portable. The sensor technology can be further developed to improve accuracy and selectivity, and the calibrations are performed using only a few calibrators to establish the correlation at specific points within the instrument's operating range. While it might be desirable to use a large number of calibrators to establish a calibration relationship or curb the time and labor associated with preparing and testing a large number of calibrators might outweigh the resulting level of performance from a level of project performance and the effort associated with the accomplishing the calibration. The instrument will provide the best performance. This is the Pleiadic colorimetric sensor design for water hardness detection, and thank you.